This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Bocek, and today we have 5 topics. First topic is the following article here. This recent article in Communications of the ACM looks back at 10 years of Docker. Well, it's a bit more than 10 years. Docker was first released in 2013 and simplified building, distributing, and running applications in isolated containers. Developers write a Docker file, build an image, push it to registry, which is explained and quickly shown here, and run it on any machine with Docker installed. And the core workflow of Docker build and Docker run has remained the same since 2013. And the article explains the technical foundations behind Docker. It describes how Linux namespaces give each container its own isolated view of the file system, networks, and processes without the overhead of full virtual machines. It covers the client-server architecture, where BuildKit assembles layered file system images and Containerd manages running containers, with the image format standardized since 2016 by the Open Container Initiative. A large part of the article covers how Docker expanded beyond Linux. By 2015, most developers used macOS or Windows, but Docker images could only run on Linux kernels, and the solution was to embed Linux inside those desktops using a virtual machine, and this ran a Linux kernel inside user process, and the Docker daemon run besides that. And a custom minimal Linux distribution called LinuxKit was built for this, containing only the components needed to run those containers. Docker for Mac and Windows was released in 2016, and on Windows, Microsoft later adopted a similar approach with the Windows subsystem for Linux in the version 2. They are running a full Linux virtual machine in the background to make sure that Docker runs as on the Linux operating system. And another interesting point was that after Apple released its M1 ARM chip in 2020, Docker needed to support multiple CPU architectures. The OCI image format was extended for multi-arch manifests, and Docker uses QEMU to translate between instruction sets during the build phase. Apple later introduced Rosetta for hardware-level instruction translation, which was integrated also into Docker or used by Docker. Today, running Intel and ARM containers side by side is a common workflow. And in our lecture, we discussed Docker and containerization in lecture 3. This article shows how important Docker as a container solution has become, even though there are many other alternatives, runtimes, and tools. Docker remains the tool most developers use today. The second article, it's the following here. A recent blog post compares CPU performance and prices across 44 virtual machine types from 7 cloud providers: AWS, Google Cloud, Microsoft Azure, Oracle Cloud, Akamai, DigitalOcean, and Hetzner. All instances were tested in a 2 vCPU configuration, and the main finding is that AMD dominates both single-thread and multi-thread performance. Intel's new Granite Rapids is a solid improvement over its predecessor, and on the ARM side, Google's Axion chip matches previous generation AMD performance per thread, making it the current ARM leader. And for on-demand pricing, Hetzner and Oracle offer the best performance per dollar. Hetzner's cheap shared core instances are the overall price performance leaders. One chart in the article shows them delivering roughly 2 to 3 times the value of anything from the big 3 providers. And it's the following chart here. When we scroll down, we see here, this is single thread performance per dollar. Here we see one Hetzner instance in red. Dark red is Oracle. And then when we look at the other Hetzner instances, so this is the CCX13, this one here, which matches here almost the standard E6 from Oracle. And we see those others outperform in thread performance per dollar. However, these Hetzner instances have limited availability, are mostly restricted to European regions, and sometimes cannot be provisioned at all. Oracle also has the most generous free tier in the industry, though given Oracle's reputation for aggressive licensing and vendor lock-in, commenters in the Hacker News discussion were skeptical about relying on it long term. Among the big three, AWS is constantly the most expensive on demand, while GCP and Azure compete closely on value, especially with their ARM and latest AMD offerings. With longer reservations or spot pricing, the big three can match or beat budget providers. One interesting takeaway is that fleet age matters, also discussed in this article. Older VM types are slower and often more expensive because providers charge more to cover higher operational costs. DigitalOcean has fallen behind because it still runs old CPUs and hasn't upgraded, while providers that offer the latest AMD or ARM chips deliver better value even at higher list prices. The article recommends avoiding old CPU generation entirely and checking what hardware you actually get, since some providers assign different CPUs to the same instance type depending on the region or timing. And I mentioned in the lecture, we discussed this, so we had the pricing, but those were the numbers from 2024, and now we have the actual numbers from 2026. The next article is about WebAssembly. It's the following here. This recent Mozilla blog argues that WebAssembly is still a second-class language on the web, despite many new features since its 2017 release. WebAssembly still cannot interact with the web platform directory. It must go through JavaScript for loading code for using web APIs. Even a simple console log call requires JavaScript glue code that re-encodes data between WebAssembly memory layout and JavaScript types. And this glue is tedious to write, so tools like WASM bindgen or mbind generate it automatically, but this adds build complexity that is language specific. Standard compilers can produce WebAssembly files, but those files won't work in a browser without the glue, which confuses developers who expect a simple compile and run workflow. Mozilla ran a DOM benchmark and found that removing the glue code reduced execution time by 45%. And the proposed solution is the WebAssembly component model, standards track proposal in the development since 2021. Components are self-contained WebAssembly artifacts that describe their API using an interface description language. Browsers would natively bind web APIs to those components without JavaScript involvement. A program could compile to a component and load with a simple script tag, no glue code needed. Mozilla is working on this with the WebAssembly community group. And in my projects, I felt the same, this second-class treatment. This is my project PrevelKit, where I have a single-page application library that compiles to WebAssembly. And this, what you see here, is the glue code, slightly adapted. I used the one for the Go libraries, and I stripped the unnecessary parts. But still, this glue code here is necessary to make your WebAssembly run. And with those web components, this would not be necessary, and I'm looking forward for these web components. The next topic are about these two articles. The first one here, these two articles addresses the same question from a different angle. How do you work effectively with AI coding agents? This first article argues that the growing docs directory many developers maintain for the AI agents is a temporary and fragile solution. It starts with a modest Claude MD or Architecture MD, then grows into dozens of markdown files as developers extract shared context. But over time, these documents rot, subtle inconsistencies pile up, and there's no way to tell when a document is wrong, and different documents change at different speeds. And the author advocates for spec-driven development, where you write a detailed specification first and iterate on implementation with the large language model, keeping you connected to the code. The core argument is that context describes intent and real-world boundaries that comes from humans, yet we manage it with plain markdown files. I disagree with the idea that inconsistencies are hard to detect. With current large language models, checking a set of documents for contradictions is just one prompt away, and it has never been easier to spot inconsistencies. The harder problem is deciding what the correct version should be, and that remains a human judgment call. The second article defines 8 levels of agentic engineering, from basic tab completion to autonomous agent teams trying to categorize the progression. I don't like this clean separation. In practice, these levels overlap, and most teams use a mix of context engineering tools, feedback loops at the same time, rather than moving through them sequentially. And the real threshold is level 6, where automated feedback loops let agents verify their own work through tests, linters, and pre-commit hooks. Once that works, level 7 and 8 background agents and autonomous teams are just extensions of the same idea. You scale what you already have. The hard part is getting the feedback loop right, not spinning up more instances. And the author also argues for using different models for different jobs, since models are biased towards their own output when reviewing their own work. And for the challenge task, when talking with students about what works best, planning first or writing a design document first, and these articles confirm that both matter, but in different ways. The spec-first approach keeps you in control and produces better result, but the context behind the spec is what actually drives quality. If your context is wrong or stale, the plan and the code will both degrade. The last topic from today are these 2 articles. So the first article here is from New York Times. This reports on how AI coding agents are transforming software development in the US. Developers now spend most of their time talking to AI rather than writing code. AI startups, close to 100% of code is AI generated. At Google, it is around 50%, a bit less than 50%. The article describes how coding has always been about layer of abstractions, from assembly to Python to open source libraries, and AI is simply the next layer, where developers describe intent in plain language and agents produce code. The job has shifted from writing to judging. One developer noted that in 4 months of heavy AI use, she started losing her ability to code by hand. Senior developers feel confident because they have decades of experience to assess AI outputs, but the concern is whether the next generation will develop the same intuition. And the second article, this one here from Sixth Tone, shows a grimmer picture from China's developer market. A programmer who used to charge 300,000 yuan for custom apps now get 20,000. AI generates over 60% of front-end work, so teams that once needed 10 people now need 4. And prices have collapsed because clients see AI-generated frameworks and assume the work is nearly free, not understanding that the real effort is in fixing vulnerabilities, refining logic, and maintenance. The article describes developers as tech janitors who spend their time cleaning up AI-generated mess. AI code often clashes with established practices, and fixing one bug frequently introduces another. A young developer who relied heavily on AI found himself unable to debug a project on his own, felt de-skilled, and left programming for a sales role. Senior developers say many junior applicants can no longer explain basic coding logic, and the article concludes that in this industry there are now no winners, only survivors. It's a bit negative article. It was also translated from a Chinese website, so the text flow is also not that smooth. But both articles describe the same shift from a different angle. The semi-automated tasks that were once outsourced, building standard apps, writing boilerplate, assembling frameworks, are exactly what AI now can handle. And if your work consisted of these tasks, you need to rethink, because this can and will be automated. The real value is in understanding what the code should do, spotting when AI gets it wrong, and knowing the domain well enough to judge the output. This year, I did not write code myself, but I produced a lot of code, and this is the new reality. Skills that were once secondary to coding, like communication, systems thinking, domain knowledge, the ability to clearly describe what you want, are now becoming much more important than the code itself. This due to generative AI.